So we want to slash down the complexity from 1 over beta to something which is just polylogarithmic 1 over beta. So if a beta is 10 power 4, I'm just looking at logarithm of 10 power 4. So that is a substantial reduction. Okay. So how do I get such reductions? Like, so how can I go about it? So one common approach, which whenever we face with rare events or tail expectations, is to kind of do variance reduction by importance sampling. So we already saw that sample average approximation and stochastic approximation are what are commonly used. Why? Because they are universal in use. As long as you have finite second moments, you can use these methods and they will give you reasonable performance. Despite the rarity, they will just, if you do enough number of iterations, you will get a convergence. The complexity is poor, but they are easy to use. So they are universal in use. That's the good part about it. So the variance reduction methods, on the other hand, are tricky. And one example is importance sampling. In importance sampling, what you would have to do is like, so under the original, this is the tail set. Under the original distribution, we are not seeing a lot of scenarios in the tail set. So what I do is I just change my distribution. That's the new distribution, which places a lot of mass in the tail set. So since I have changed the distribution, of course, my answers are going to be wrong unless I kind of like remove the bias by multiplying by the likelihood ratio. So I just reweight the samples by the likelihood ratio, and that gives me a good way of estimating the rare objectives. So the two challenges which come here, the first thing which would have come to your mind is, hey, how would I arrive at a good change of distribution in the first place? So for a given problem, if the problem is involving hundreds of variables, it's in 100 dimensions, how would I know what is a good change of distribution to begin with? That is the first question that will come in your mind. And another question is, if you're doing optimization, at different points, you may have to use different change of distributions. So what is a good change of distribution at a particular decision point, theta 1, may not be a good decision point for like theta 2. And if you look at the asymptotic variance of the stochastic approximation method or a sample level distribution, you will see that the asymptotic variance is kind of like minimized by the variance at the optimal decision, which I don't know. So there is a certain circularity. If you want to use the right change of measure, if you want to use the most appropriate change of measure, which minimizes the variance, then you would need to know the solution to the optimization problem to begin. So there is a circularity issue, and these are the couple of challenges, right? So first, maybe I'll just spend a little bit of time dwelling on the challenge one first. So the plan for the rest of the talk is the following. So having introduced the key challenges, I'll dwell first on the challenge of how to arrive at a good change of distribution for the type of problems that we are interested in. And then I'll kind of like, expand upon the challenge and then kind of give a solution, like a key observation which allows us to propose a very novel sample. And then we will substantiate with the theory. Like after introducing the sampler, we will substantiate with the theory of how large deviations, which is particularly of interest to regular variation belongs to heavy tails. So how regular variation and large deviations can be kind of like used to substantiate why this importance sampling works, and then we will do variance calculation. Yeah. So this is a plan for this. Any questions? Okay. Fine. So how easy it is to come up with the change of distribution? That is the first question. So it is well known that the best distribution that you can choose for importance sampling is the conditional distribution. It is often called as the zero variance distribution. So basically, you look at the distribution of X conditioned on L of X. If at all you can sample from that, that is the best distribution that one can use. So, but in practice, it's not possible to sample from it. So what you do is like you kind of like look at distributions which approximate this well. So here, like I look at the zero variance distribution for a specific loss and a specific distribution combination. Here I have loss given by a ReLU neural network. It's a piecewise linear function, and X is a multivariate normal random variable. And in this two-dimensional picture, what we see is like the losses, the conditional excess loss samples are getting concentrated in these two regions. That's what we are seeing. Now, okay, then a good importance sampling distribution should concentrate mass in these two regions. Now, if I change my distribution without changing the loss, what has happened is like I change the distribution, not even the joint, I just change the marginal. From normal, I change it to variable. and suddenly the points at which it should concentrate has changed significantly. Right? Now, if you go to exponential marginals, you see again the points at which it concentrates has changed. So this is in 2 dimensions. When my distribution changes, when my marginal distribution changes, you kind of like see that the conditional excess loss samples are concentrating in different regions. And my importance sampler has to somehow magically know where this concentration is happening for it to be effective. Now think about a 100-dimensional problem. So this is 2 dimensions, okay. But in a 100-dimensional problem, if you have to find exactly where the conditional excess loss samples are concentrating, that's very hard. That's pretty hard, right? So that's the fundamental challenge. How do I find good changes? A good change of distribution is instant dependent on a highly non-trivial manner. It depends on the loss at your hand, and it also depends on the distribution at your hand in a highly non-trivial manner. And that's the issue. And if this is the difficulty, what gives us hope? What gives us hope is there is a beautiful body of work in rare simulations literature, where in stylized problems, in highly stylized problems, like sums of random variables, maximum in a single server queue, in highly stylized problems, we have had excellent variant reduction. The gold standard has been achieved. And how this is achieved is typically by doing large deviations analysis specifically for that problem. So what I'm showing, I'm not reviewing the literature in detail here because of the lack of time, but like here, what I'm showing is like, different problems. One is a portfolio VAR estimation, one is credit risk estimation, one is sums of random variables, another is like distribution networks and so on. You have different problems and you have different distributions. And for each of these, literature has required us to kind of like do different change of measures by doing different large deviations analysis specifically for each of the problem. You do large deviation analysis specifically for each of the problem, come up with a good change of measures specifically for that problem, and that becomes that each of these are nice contributions in that aspect. So one surprising thing is like what works here will not work here. Right? If you change the problem or if you change the distribution, you need to write a new data. Right? Okay, so that's the problem. You have to do a large variance analysis for each and every problem. And this works only for stylized problem. This is our starting point, but then like we want to make important sampling scalable. This is our starting point. This is what gives us hope. Now, how does this work typically look like? You start with a model and then propose a good alternate distribution family to begin with. This is typically informed by the large variance analysis. So in the literature, this has been via exponential twisting. If you have sums of random variables, this is via exponential twisting. This could be via hazard rate twisting. There are many methods. Sometimes you will have to do mixtures based on dominating points. So each large deviations analysis is different, and you will have to inform a good alternate distribution family based on these large deviations. That is what is the first step. And the second step is like once you inform the family, you have to find a good parameter, good distribution choice. And for that, you may have to solve a quadratic program, you may have to solve a mixed integral program, or you may have to solve a dynamic control problem, and so on. So if you want to get a good importance sampler, this is the workflow which is typically involved. So sometimes like finding a good importance sampling distribution itself will require you to solve the non-trivial control problem. Right? That's the challenge. So how do you overcome this challenge? So can we have this impressive sample reduction that we have been available more broadly? And for this, first, we make a diagnosis of the difficulty. So I presented the difficulty and why this difficulty is happening. The difficulty is happening in our view. The difficulty is happening. It persists. The difficulty persists as long as you are seeking an explicit prescription for the change of the distribution. If you want to say, hey, this is the distribution I want to use, then the difficulty is going to be persisting because the good change of distribution is going to be a non-trivial function of your objective as well as the random variables. So what we are doing here, here I'm going to make a key observation. So maybe these are the 2 slides which are the most important for the talk. So you are familiar with this picture now. This picture says that the concentrations are happening in different, for different problems, the concentrations happen in different regions. You are familiar with this picture. So what is striking is that the concentration is replicated at significantly lower levels of rarity as well. So this is at 10 power minus 4 or 10 power minus 5. This is what is the concentration that we are seeing for the excess loss sample. And at a 10 power minus 2 rarity level, this is where the concentration is happening. Likewise, in the same problem, the concentration is mirrored. So how the concentration happens at higher levels of rarity is mirrored in lower levels of rarity as well. And that's what we want to explain. So typically sample average approximation will ignore all these blue samples and will make use of the red samples alone. But the blue samples occur 1,000 times more often than the red samples. So can we use these blue samples to inform how the concentration for the red samples should look like? So in each of the problem, there is a similarity, the self-similarity in how tail events are happening. Can we exploit that similarity? That is the key idea. So we change our question from, instead of asking a good change of distribution, we change our question. Instead we ask, is there one transformation which can induce each of these red profiles in each of the problems when applies to the blue samples? So for all the three panels here, I'm looking for the same transformation which will induce the right concentration in each of the respective problems. So is that possible? There is no reason that such a transformation should exist. So at a caricature level, the literature has been largely approaching this question like this. For a model 1, find a good sampling distribution. For model 2, find a good importance sampling distribution. For a model 3, find a good importance sampling distribution, and so on. What we are seeking here is instead, can you find a transformation T, which is fixed for all the models, but its push forward is a good importance sampling distribution. May not be the best, but it still is a good importance. And our answer is like, yes, that is possible. And a simple transformation like this will do for a large variety of problems. So for what variety of problems and so on, what variety of distributions I'll introduce next. But this simple algorithm, this simple transformation will be. So what it says is that, so you take my samples, X is my vector valued sample. It's a multidimensional, it could be hundreds of dimensions. So I take my vector valued sample and stretch each component by a factor like 2 or 5. This S is a scalar stretch factor. But in each direction, the exponent here is a vector. So in each component, I'm going to stretch it differently. Each component is getting stretched differently. How differently? So this is my exponent. So the exponent can be read as logarithm of x divided by logarithm of norm of x. So if my x1 component is already large, the norm will also be large. So the exponent will be close to 1. But if my x1 component is small, the norm will be small. The norm will be large, but the x1 component will be small, in which case the exponent will be silent. So what is happening is the directions which are already large, the components which are already large are being stretched further, and the components which are not large are not stretched at all. They are just left as it is. So this is not a naive stretching, but stretching informed by the samples themselves. Right? Okay, so in action, what this is doing is like, so applying this transformation to these samples, this is how the concentration profiles match. I apply this transformation to this sample, this is how the concentration profiles match. So the same transformation will do the job for regardless of where your concentrations happen. And that's the key idea.
So, but you have to believe that this is similarity.
This is self-similarity, yeah.
Self-similarity, yeah. How to check it?
Yeah, how do you check? So I know, okay, so for this problem, I'm assuming that you know the distribution. You are given the model. You are not doing learning here. There is no learning here. You know the distribution. If the distribution is satisfying certain conditions, which I'm going to introduce next, then the self-similarity. I'm going to introduce that next. Thanks. So this is what is happening. In this problem, the rare event is happening because both the components are becoming large. In which case, the exponent is 1, 1, concentrating as 1, 1, which means both the components are being stretched. On the other hand, here, the excess loss events are happening because one of the components is becoming large. This is like the heavy tail case. This is the light tail case, this is the heavy tail case. So in the heavy tail case, like it's happening because one of the components is becoming large. And so the exponent is concentrating at 1, 0 or 0, 1. Right? Yeah.
But you wouldn't care about the loss function, how the loss function behaves?
How the loss function behaves is already kind of determined by these blue samples. So these blue samples are excess loss for that loss. If my losses had changed, the blue sample will also look different. So they already capture. I don't have to be doing that arithmetic myself. The samples inform it. Thank you. So if I have to estimate my objective, it will be a relatively simple algorithm. I don't have to do any complex 3-step procedure and so on. I just obtain samples with the original distribution, apply the scaling, the stretching based transformation, compute the likelihood ratio computation is like, it's just a transformation. So Jacobian comes in, it's a undergraduate like kind of exercise. And then you just kind of like reweigh your expectation with the likelihood ratio. That's it. So the one parameter which has to be identified here is the scalar stretch factor. Is a scalar stretch of 2 good or is a scalar stretch 5 good? Like that, we don't know beforehand. We do like the theorems that I'm going to present give some idea. But as such, it's ideal to be done by cross-validation because the results are asymptotic. It's ideally done by cross-validation. Okay. If I have to do a risk minimization, then what I do is I just incorporate the same procedure in a stochastic gradient descent step or a stochastic approximation step. So what I do is I start with some initial batch of samples. I apply the stretching-based transformation, and then I do a stochastic gradient descent. But except that, with the new samples, I do the important samples, not with the original samples, so that the indicators are going to be turned on more often because the important samples are stretching, putting more and more mass in the rare set. These indicators will be turned on more frequently. So, and then this will be having less variance. So the gradients will be better behaved. The gradients will be more informative in every step. And then once in a while, you update the scalar stretch factor. You just kind of like do a cross validation to check what would be a good scalar stretch factor to be used at that point of time. You do that once in a while. So this 2 steps, just a straightforward stochastic approximation, or stochastic gradient descent, but you just reweigh with the likelihood ratio. That's all is the difference. Okay. So when is this simple algorithm efficient? Then the pattern is via some tail modeling and large deviations. How much time do I have for that?
Around 15 minutes.
15 minutes.
Total, inclusive of
Questions. Thank you. So when is this simple algorithm efficient? I'll answer this now with the large deviations and tail modeling. So when can we have this beautiful mirroring, self-similarity in how tail events happen? Under what assumptions? For that, I think there can be a broader variety of assumptions, but here I'm just kind of like, for the sake of simplicity, I'm focusing on some simpler assumptions. So let F denote the probability density function of the random vector X. Now, if the random vector is light-tailed, I'm requiring that the logarithm of the density to be regularly varying. If it is heavy-tailed, I'm requiring F itself to be regularly varying, the density itself to be regularly varying. These are multivariate densities, so I'm talking about multivariate regular variations, right? So what do I mean by regular variation here? So this is my regular variation. Phi has this nice property. It's polynomial-like, of course, with a slowly varying modulo component. So phi, the function which is regularly varying, behaves like this. So there exist scaling vectors, like scaling vectors, which will have this property. So this is what is regular variation. I'm not expanding on it very much because this audience is so familiar with regular variation and multivariate regular variation. That's why I'm not expanding. But if something is not clear, please. But for someone who hasn't heard a great deal about multivariate regular variation, the easiest way to think about could be these functions phi, or like approximately like polynomials, homogeneous functions or polynomials. So in the case of heavy tail, in the case of light tails, I'm requiring the logarithm of the PDF to be regularly varying, which means a canonical example would like something like Gaussian would kind of easily kind of be a good example. So if you see multivariate normal, the exponent like the logarithm of f is proportional to x minus mu transpose sigma inverse x minus mu. This is clearly a degree 2 polynomial, and it's going to satisfy this condition with qn to be n power half and so on. Right? It's a polynomial, and we can easily check the regular variation. So this limit function is what is the shape phi star. So this phi star informs how does my tail distribution contours look like, right? In the case of heavy tails, I'm requiring that this f itself is like regularly varying. So the same distribution, the same assumption works for regular variation, but then in the example of heavy tails would be like, for example, the t distribution multivariate. The phi itself is polynomial. So several problems that we use in practice, several models in risk management that are being used will satisfy typically this property. Multivariate normal, multivariate T, elliptical densities, exponential families, log concave densities. If you prefer using marginal distributions with copula, then Gaussian copula, T copula, Archimedean copula, many of the models that we use in practice will satisfy this. I'm not making a parametric assumption. I'm making only a semi-parametric or non-parametric type of, which says there is regularity in the tails. Like as I go deeper in the tails, like I'm not having kinks in the tails, there is a sufficient regular behavior. That's what this assumption says. And this phi star is the limiting shape of the densities. And what is the assumption on the so what does this give me? What does this give me? This assumption gives me a certain large deviations principle, which provides me a basis to go and study how these rare events are happening and how can I justify variance prediction and so on. Yeah.
Just a question. Could it, I mean, in regular varying, you could have like slow variation included.
So regular variation, you can have slow variation, not a problem.
I mean, it's not, I mean, alpha equals 0, it does not. Okay.
Yes.
So, but this is for density, not for distribution factor.
Yeah,
It's for
thanks. Yeah,
density.
this is
It's
for
a big difference. Yeah.
There's a big difference. Yeah. Thank you.
Yes, but in the light tail. Okay, fine.
Okay, thanks. Okay, so there is a large deviations principle which will be satisfied, and this is what provides us the machinery to kind of like study the variance. So what does the large deviation principle says? Like, so if I look at the scale, the x over qn, if I look x in a certain tail set, this qn is a scaling. It takes a tail set and it looks in that direction. It looks at a tail set as n goes to infinity. This set can be approximated by some small balls. The typical large deviations argument, you can approximate it by small balls. And in each ball, the density is going to be like this. In each ball, the density is going to be like this. And if you use the Laplace's principle, only the dominating exponent will stay. So the dominating exponent will stay when you are adding e power minus 1 plus e power minus n plus e power minus 2n, e power minus n alone will stay. The rapidly decaying ones will not stay. So the exponent will be dominated by the infimum over this rate function, the smallest point over the rate function. So this becomes the rate function. You easily get a large deviations principle with this traditional large deviations argument. Nothing serious here. And what you also get is an explanation for the self-similarity behavior. So this is Qn times A set. And if you look at a scaled version, a suitable scaled version of that set, which is 2 power 1 over alpha A. So alpha or the regular varying indices of each of the marginals. So this is each components are being stretched differently for the set A. And then the same arguments will apply, and then you will get the self-similar. Like so you see the exponents are matching here. The exponents are matching. So that's the self-similarity. Right. So for a suitably scaled set far in the future, further in the tails, the earlier in the tails can explain what is happening further. Self-similarity is how tail events are happening. And this is the assumption on the distribution. So we make a semi-parametric or non-parametric assumption on the distribution, which only controls the shape. Right. And which only kind of like, there is a great degree of freedom on the shape. Only you have to be sufficiently regular as you go deeper and deeper in the tail. That's our assumption on the distribution. What is the assumption on the loss? We could have as well worked with a regularly varying loss, multivariate regularly varying loss. But we just, for simplicity purpose, we chose with the homogeneous, approximately homogeneous loss functions. And then what type of losses do satisfy this? Piecewise linear quadratic functions, optimal values of linear programs, ReLU neural networks, all of them satisfy this assumption. So all the examples that I covered initially will satisfy this assumption. So the losses are okay. The distribution is kind of like what I specified. Then what do I get? I do get that, like you have this limiting density has the shape V star and the limiting loss shape is L star, and you can get an explanation for how the rare event is happening. And what is the explanation? The explanation looks like this. So you look at the limiting shape V star, and this is the blue is the limiting shape for L star. So the way the rare event can be explained by how this particular intersection is happening, the earliest point where the phi star happens to intersect with the L star, the level sets of the L star, by limiting this. So these are the points where the intersection happens the earliest, and those are the cheapest way for the rare event to happen, and that is what is being mirrored in the tail samples that I already showed. So in the pre-limit, what you are seeing as concentration is explained by this intersection, right? Now, if you change, if you kind of also look at the lower levels of rarity, the homogeneity will explain, the homogeneity of these functions phi star and L star will explain why these are happening at congruent points. The self-similarity is being mirrored in this picture as well. right? So the self-similarity can be very well explained by the large deviations, and you can get neat asymptotics for how the tail events are happening, right? And if you change the distribution, again, the explanation can be provided the same way, pretty much where the phi star is intersecting with L star, that provides the explanation. So then in this picture, our question of can you find a transformation becomes a simple question of can you find a transformation which kind of translate any possible rate point, any possible x point on this dot point on this set to x, the respective congruent x point on this set. So that's what the question becomes. So the question on large deviations picture is relatively easy to answer, and we can show that if you want to have that property, then T of x, the transformation, you will have the preserving property if and only if my transformation is of this form. And that form is what we had initially identified as the transformation I'm going to use. So an explanation for why the importance sampling transformation that I proposed initially can be obtained from the congruency of this phi star and L star. So this is the transformation which works, and the one that I exhibited initially asymptotically will kind of converge to the same transformation, and that's the explanation for why a transformation would work. So with this large deviations backing, one can go and actually show that minimizing this tail risk measure with stochastic approximation with the algorithm that I showed initially, like where the gradients are being kind of like informed by importance sampling distribution, and you are reweighing by the likelihood ratio. That is log efficient, the gold standard I wanted to reach. By log efficient, what I mean again is like the number of samples required or the number of iterations required to achieve a certain accuracy. Without importance sampling, it's like 1 over beta. But on the other hand, beta is a small number, like 10 power minus 3 or 10 power minus 2 or 10 power minus 5. So this is humongous, but that can be made significantly small, polylogarithmic in 1 over beta. And that's what you can show with the large deviation channel. So you get the log efficiency, and further, within the class of samplers that I considered, we do achieve the adaptive scheme that I introduced, like thanks to some recent work of Henry Lamb and his co-authors. So we can show that like it kind of like achieves the smallest possible asymptotic variance, which is possible within that family. And numerically also here I have a simple illustration with some 15 assets. What we see is like without important sampling, the sample complexity indeed increases when your beta becomes smaller and smaller. So here I'm trying to minimize the conditional value at risk subject to meeting some return requirements. On the other hand, with important sampling, it stays roughly like it doesn't grow. It doesn't grow. And you see that as we become deeper and deeper at lesser levels of at higher levels of rarity, we see a savings of like 25 times or more. Like if you go even farther, in rarity, the savings will increase. Right? We do see the log efficiency in practice. And then one question could be like, hey, how important is to get the stretch parameter correct? So you are having this, you are blowing up the samples deeper in the orthant. How important it is to get the stretch parameter correct? Here I am kind of like showing the stretch parameter is in the x-axis and the y-axis is the logarithm of the variance. And what we are seeing is it's relatively flat. The variance is relatively insensitive to the choice of stretch parameter. So all my results I overlooked, I missed it, sorry. So the results require my level U to be the stretch factor to be certain. Like so, it has to be like growing only. It has to be growing at the level of at a slowly varying function of beta. So it will require the results are established when my stretch factor are kind of like a slowly varying function of beta. And in practice, what we see is like it's pretty much. It's not too sensitive to the choice of the stretch factor because these are black box importance sampling. Even if I get the stretch factor kind of a little off, what I'm doing is I'm only boosting the likelihood of scenarios deeper in the tail. So I'm not going to be very worse off. So it works out reasonably well. So in this talk, just to summarize, we had this extensive workflow for identifying a good importance sampling distribution. And what we have done is like, we again have used large deviations. Using which we kind of automate this workflow to some extent. You don't need to be doing instance-specific large deviations for every single problem. Like so, you can use a black box sampler and then get a good change of distribution. And the key idea is to not explicitly search for a good importance sampling distribution. That's going to be a futile effort. Instead, like just implicitly try to induce a good change of distribution, and that works out reasonably. And this is the simple transformation. And this, to the best of our knowledge, this is the first black box approach to making important sampling work for rare events and optimization and so on. It can be easily embedded with use in stochastic approximation. So with this, the couple of papers that kind of explain this are here. And then thanks a lot for your attention and thanks a lot for this opportunity. I'll be happy to take it.
Few minutes, maybe some questions.
Can you use multiple levels? I think I asked this maybe last year, but can you use multiple levels? Because now you use like a smaller level and then boost it to get higher level. Can you use several smaller levels?
Certainly, and there is nothing which is going to.
No, but do you gain anything from trying that? Or
So we have tried doing a mixture for the stretch parameters. The stretch parameter, there is a mixture distribution. And we do see somewhat improved performance with that. Like, so it's just that our key, there are n number of ways in which this sample can be kind of enhanced.
Sure.
And this is certainly one way, and that's what, like, after talking with you last year, we indeed did try this, and it indeed does work out. It works out better. But my feeling is that, like, so we kind of have intentionally wanted to keep it simpler because optimizers, like, when they kind of want to solve, they like SAA, sample average approximation, a lot because it's simple and universally used. So the simplicity, we just want to retain it so as simple as possible. So yeah, that's why we have, but it does better.
Right.
Great question.
Question?
Quick question. So essentially, you increase the size of sample size, yeah, it's significantly, yeah. To some extent, you can. It helps to increase the sample size. You can count blue two, yeah, blue samples too.
Yes. So the number of effective samples falling in the rare region is increased. Yes, that's correct.
Exactly, yes, and gives you, it improves the performance, yeah.
Yes, and that I can adjust for that mistake by reweighing the likelihood ratio. That is very cheap, so no problem.
Yeah.
Okay, let's thank the speaker and we get the.